In the previous parts, we have introduced the virtual work principle. We introduced the equations of the virtual work. We introduced we presented some examples in which we showed the external virtual work is equal to the internal virtual work for beams and for continuum, for general continuum. We also presented two applications for the principle of virtual work. And the two applications were as follows. The first application, so the applications that we produced for the virtual work, the first application was finding the reactions of statically determinate supports, for statically determinate beams, so we had for example, we had a simple beam, load, we moved the beam by an arbitrary displacement, and we wrote the equation, the external virtual work is equal to the internal virtual work, and from which we found the reactions. The second application, which is you are using for so your structural analysis courses, is finding displacements at specific points. And so this is what you do in 372, for example, CIVI 372, where you have a beam with loading, and we're interested in a displacement at a specific point. What is this displacement? Then I set up a new configuration for the beam. In the new configuration, I put a unit load at this particular point, and I find the reactions, the bending moment, and everything for that new configuration. And by applying the principle of virtual work, utilizing the displacement here in this configuration as a virtual displacement, utilizing this displacement as a virtual displacement, and these configuration, utilizing the forces from this configuration, you come up with you write the equation that states external virtual work is equal to the internal virtual work, from which the external virtual work is equal to 1 multiplied by the unknown displacement. Internal virtual work is equal to m naught m1 over EI integrated over the length. And as I said, I'm not going to ask you about this application in your exams because you already studied in 372 in more details. Now, in general, right now, if you're interested in the displacement or in the solution of a structure, you actually input this in a software. So this application is no longer, is really, people don't use it anymore because you only get the displacement at a specific point. But right now, if you want to find the displacement or the bending moment, the shearing force, and the displacement of the structure, you put it inside a software. The software does the analysis and gives you the displacement at every point, not just displacement at a specific point, but it gives you the displacement at every point in the structure under this load. So these are structure analysis softwares. And utilizing something called the stiffness method. Now, for a continuum, however, we still use the virtual work, which is the basis for what we have been talking about, which is the finite element analysis method. So, if I have a continuum, usually I'm interested in where does this continuum go? What is the displacement of this continuum after applying all the loads? so I'm interested in this. And to do this, we utilize the principle of virtual work. To actually find an approximate solution to the differential equation of equilibrium. Now, as we talked about in chapter 4, the differential equation of equilibrium is actually very complicated, and it's usually very difficult to find a solution to an exact solution to this differential equation of equilibrium. And so that's why we utilize the principle of virtual work to find approximate solutions, and this is the subject of today's part. How to find an approximate solution using the virtual work method. So let's try and understand now what is the difference between an approximate solution and an exact solution. And we're going to do this using an example. So in this example, we have a beam with a concentrated load in the middle. And we need to use the virtual work method to find the displacement shape for the shown beam. And we want to compare with the exact solution. So let's try to understand first what's the exact solution and what is the approximate solution. So the exact solution is the solution that to the differential equation of equilibrium. So because this beam has a concentrated load here, I will have to divide this beam into two parts. For the first part, it has a reaction here, and there is a shear at this point and a moment at this point. I'm going to call this M left, shear left, and the other side of the beam I have R2. R3 is 0. I'm not going to worry about R3. And here I'm going to call this V right and moment right. And because I isolated that beam, I isolated the left part and the right part, I have to include this concentrated force. So I'm going to include this concentrated force by looking at it this way. This is P. Because of equilibrium, this is VR. This will be equal to VR. And if this is VL, then this will be equal to VL. And if this is ML, this will be equal to ML. And this will be equal to MR. And now let's write the differential equation of equilibrium. The differential equation of equilibrium will be different, or I'm going to have to solve the differential equation of equilibrium twice. Once in this portion and once in the other portion. So in the first portion, I have EI, D4, I'm going to call it Y1, equal to 0. And so EI, D3, Y1, by dx1 cubed is equal to C1. Is equal to C1 x1 plus C2, and so on. So I'm integrating on this side, and finally EI Y1 is equal to C1 x1 cubed over 6 plus C2 x1 squared over 2 plus C3 x1 plus C4. So on this beam, on this portion of the beam, the displacement function has those four constants, C1, C2, C3, and C4, that we need to find from the boundary conditions. On the other side, there's another displacement function. I'm going to call it d4 y2. So I'm going to call it y2. And doing the same thing, I'm going to get the EI y2 is equal to, instead of now those C1, C2, C3, C4, I'm going to call it D1. These are the different constants. D1 x1 cubed over 6 plus D2 x1 squared over 2 plus D3 x1 plus D4. So I have 4 constants on the right and 4 constants on the left that I need to find using the boundary conditions. So what are the boundary conditions? At x there I need 8 boundary conditions. The boundary conditions are 1 at x1 equals 0, y equals 0. The displacement at the first point is equal to 0. The second at x1 equals 0. The moment m1, which is the second derivative of y1 with respect to x1 squared, equal to 0. And the third boundary conditions. So I'm looking at the boundary conditions here and here. So at the end I have the displacement and the moment is also equal to 0. So at x1 equal L, the displacement function y2 is 0. And at x1 is equal to L, the moment, which is the second derivative of the displacement function, is also equal to 0. So these are 4 boundary conditions. I need 4 more. I'm going to utilize the middle portion, or the conditions in the middle portion of the beam. The conditions of the middle portion of the beam are as follows. Looking at this area, you'll find that the moment on the left is equal to the moment on the right. The displacement on the left is equal to the displacement on the right. The rotation on the left is equal to the rotation on the right. And the shear VL, V left is equal to P plus V right. And so those 4 boundary conditions, I'm going to include them. So M2 is equal to M1, or M left is equal to M right. Y2 is equal to Y1. The displacement on the left has to be equal to the displacement on the right. And at x1 equal to L over 2, again theta 2 is equal to theta 1. And finally, at x1 equal L over 2, I have the shear V left is equal to P plus V right. 8 boundary conditions. Solve the 8 boundary conditions and you get a displacement function that looks like this. Y is equal to one of the following. P x1 over 48 EI multiplied by negative 3L squared plus 4x1 squared. And this is true when x1 is between 0 and L over 2. So y1 is equal to this function. And y2, which is the displacement on the other half of the beam, will look like this. PL minus x1 divided by 48 EI multiplied by L squared minus 8 x1L plus 4 x1 squared. And this is when x1 is between between L over 2 and L. So basically, you get the following. This is the beam. The exact solution, exact because it's the one that I found by solving the differential equation of equilibrium, has a certain function here. This is called y1, and another function here called y2. And these two functions are shown as here. This is y1, and this is y2. And so this is what we call the exact solution. Now, to find an approximate solution, the next step is to try and find an approximate solution. To find an approximate solution, you have to always assume something. Whenever I say I'm going to find an approximate solution, you have to assume a shape for this approximate solution. And the nice thing about an approximate solution is I don't really care about discontinuities. When you look at this exact solution, the displacement on the left and the displacement on the right are two different functions. They're not the same function. However, for an approximate solution, I don't care about the discontinuities. For an approximate solution, I don't care about discontinuities. And I can say, well, assume y approximate, anything I want, and I think that for me, an approximate solution that's good enough has a cubic shape. A0 plus A1 x1 plus A2 x1 squared plus A3 x1 cubed. And the objective now is, what can I choose for these numbers, or for these constants? What is the best numbers I can use for A0, A1, A2, and A3? And I can find A0 and A1 and A2 and A3 by satisfying, so find A0, A1, A2, A3 by satisfying certain criteria. And the criteria are as follows. 1. Boundary conditions of the beam, or the displacement, boundary conditions, displacement and rotation. Conditions of the beam. So the first thing I have to satisfy is the boundary conditions of the beam. So this approximate solution has to make sure that the displacement on the left here is 0, the displacement on the right here is 0. And the second thing that it has to satisfy is the principle of virtual work. So if I satisfy this, I'm happy that this solution is, I know it's not exact because the exact solution is a discontinuous function. Or the exact solution is made out of two functions that are separated at this point. But I'm choosing an approximate solution that is smooth and continues throughout the whole beam. Okay, so let's now use these two criteria to try and find A0, A1, A2, and A3. So first, satisfying the boundary conditions. So to satisfy the boundary conditions, first we say at x1 equals 0, I have the displacement equals 0. So let's just draw the beam here just to remember what the boundary conditions were. I know here the displacement is 0 and the displacement here is 0. So I'm going to just use y approximate just to remember that I'm now working in the approximate solution. I'm trying to find that approximate solution. Y approximate is 0, therefore A naught, the approximate solution, which is A naught A1 x1 plus A2 x1 squared plus A3 x1 cubed equals 0. That's when at x1 equals 0, which leads me to A naught equals 0, which leads to A naught equals 0. So this is boundary condition 1. Boundary condition 2, at x1 equal L, the approximate solution has to also be equal to 0. Okay, so A1L plus A2L squared plus A3L cubed is 0. Therefore A1 is equal to negative A2L negative A3L squared. Okay, I'm going to now write the approximate. Therefore, the approximate solution after satisfying the boundary conditions is as follows. Y approximate is equal to A naught is 0, A1 is going to be replaced with negative A2L, negative A3L squared, multiplied by x1, plus A2 x1 squared, plus A3 x1 cubed, and I'm going to just take A2 as a common factor, and it will look like this: A2 x1 x1 minus L plus A3 x1 squared, no, x1, sorry, multiplied by x1 squared minus L squared. And you can see that it indeed satisfies the boundary conditions. When x1 is 0, y approximate will give me 0 because this is multiplied by x1 and this is multiplied by x1, so y approximate will be 0. And when x1 is equal to L, so I'm going to substitute L minus L is 0, and L squared minus L squared is 0. So y approximate satisfies the essential boundary conditions of the displacements on both sides of the beam. And so now I'm left with two constants. What is A2 and what is A3? So I need another criteria to satisfy, and this other criteria is the principle of virtual work. Now, what does the principle of virtual work states? It states from equilibrium, which is what we're looking for, the equilibrium equation. We're looking for a solution to the equilibrium equation. The internal virtual work is equal to the external virtual work, or in other words, the integral of EI d2y by dx1 squared multiplied by d2y star is equal to the work or virtual work by external forces, which is basically equal to the forces multiplied by the virtual displacement y star, corresponding y star. Each force, external force, multiplied by the corresponding y star. Now, so to satisfy the principle of virtual work, I need a virtual displacement. So what is y star? What should I choose for y star? As we said when we talked about the principle of virtual work, I can choose anything for y star. But to make life easy, I'm going to choose y star, to be similar to y approximate. So I'm going to choose y star to be equal to A2 star x1 minus L plus A3 star x1 squared minus L squared. So what did I do? I just chose a y star. I looked at the approximate displacement that I'm assuming, and I made it a virtual displacement by changing the numbers that I can change, which are the numbers that I don't know what to choose for, which are A2 and A3, those constants. And after doing this, just substitute into the equation. And instead of y, I'm going to use y approximate. Now in the equations, I've got all these d to y. I have to find the second derivative of these. So dy star by dx1 is equal to 2a2 star x1 minus a2 star L plus 3a3 star x1 squared minus a3 star L squared, and the second derivative of y star with respect to x1 is equal to 2a2 star plus 6a3 star x1. And similarly, the second derivative of the approximate solution that we're looking for with respect to x1 will also be equal to 2a2 plus 6a3 x1. Okay, and now I'm going to substitute into the equations of virtual work. This is the beam, and these are the external forces acting on the beam, and I have y star, the virtual displacement. So the internal virtual work is equal to EI the second derivative of y with respect to x1, so 2a2 plus 6a3 x1 multiplied by the second derivative of y star, so multiplied by 2a2 star plus 6a3 star x1, and this is all integrated over the length. So the internal virtual work is equal to this. When you do the integration, you'll get EI multiplied by 4a2l plus 6a3l squared multiplied by a2 star plus ei multiplied by 6a2l squared plus 12a3l cubed a3 star. So this is the internal virtual work. Now the external virtual work is equal to the forces multiplied by the corresponding reactions. First I have P acting downwards, negative P, multiplied by the y star at x1 equal to L over 2, so which is equal to negative P, multiplied by, where's y star? This is y star, and now I'm utilizing y star when x1 is equal to L over 2, so this is equal to negative a2 star L squared over 4 minus 3 a3 star L cubed over 8. Plus the reactions multiplied by y star at x1 equals 0 and x1 equal L. But this, when you substitute, you'll find that this is 0. Because y star is 0 at the support, because y star is 0 at the support when the reactions do not do any virtual work. Okay, so now we're going to say the external virtual work is equal to the internal virtual work. So let's look at both equations. The internal virtual work is equal to a number multiplied by a2 star and another number multiplied by a3 star. And the external virtual work is also a number multiplied by a2 star and another number multiplied by a3 star. But because y star is arbitrary, this virtual displacement is arbitrary, we get two equations. And the first equation is ei 4a2l plus 6a3l squared equal to p l squared over 4. That's the first equation. I found what's multiplied by a2 star from the internal virtual work and what's multiplied by a2 star from the external virtual work. I said they have to be equal. And also, so this is multipliers of a2 star. And I'm going to do this again, multipliers of a3 star. Here I'm going to take ei multiplied by 6a2 l squared plus 12 a3 l cubed will be equal to 3 p l cubed over 8. And solve two equations and two unknowns, a2 and a3. These are the unknowns that I'm looking for, a2 and a3. You'll find that a2 is equal to pl over 16 ei, and a3 is equal to 0. And so the approximate solution which is equal to a1, a2 x1 minus L plus a3 x1 squared minus L squared. The approximate solution has the form, this is 0 and a2 is equal to pl over 16 ei x1 minus L. So let's recap what is it that we did from the beginning of this problem. We have a beam with a concentrated load P, and we found an equation, y1 and y2, that are the exact solution to the differential equation of equilibrium for this particular beam. And then I utilize the principle of virtual work to find a different displacement. This different displacement is approximate, and it's only it's a cubic function. It's not divided into two equations, one on the left and one on the right, and this is why approximate has this shape. And if you now substitute, let's say P over EI is 1, and use L is equal to 1, then you'll see the following. If this is x1, and this is the displacement, you'll find this is the approximate y approximate, and the exact, which is made out of y1 and y2, will be something a little bit more. They're not exactly the same, but they're close enough. Now, if you don't like, if you find, so in any approximate solution, if you think that these are too far apart, then you can increase the order of your approximation. So in this example, we used y as a cubic function. If you don't like it, or if you think it's not close enough, if approximation is not close enough, then we can use higher order approximations, higher order functions. And so we can use the approximate solution as a knob plus a1x1 plus a2x1 squared plus a3x1 cubed plus a4x1 power 4, and so on, until you're satisfied that this is a good approximation. And so this is exactly how the finite element analysis method is actually implemented, using the virtual work and using some approximations for the displacement of the structure. We start with an approximation and we're looking for these constants, and so we utilize the principle of virtual work, equate the internal virtual work with the external virtual work to find estimations for these constants for the approximate solution. Now, in the next lectures, the last bit of this course, we're going to introduce a different method by which we also find approximate solutions to the displacements of a structure, and these methods rely on the minimization of the potential energy of the structure. But the methods in the next section are equivalent to the principle of virtual work for linear elastic structures, and so they actually produce the same equations, but we're not going to have to prove any of that. You just have to know the difference between how to utilize the principle of virtual work to find approximate solutions, and how to utilize the principle of minimum potential energy for conservative systems to also find approximate solutions.